Morning to everyone. Morning to everyone. Morning to everyone. Try to share the session. Morning to everyone. Try to share the session. Try to share the session. Am I audible? Please check my audio once. Please check the audio once, guys. Am I audible? Morning. Afternoon. Good afternoon to everyone. Please check my audio. Confirm my audio. Am I audible or not? Good afternoon to everyone. Yes, it is audible, right? Yes, it is audible, right? Now in this session, we are going to discuss about protection of the SCR, protection of the Thyristor. How can we protect the Thyristor, right? In this session, let us discuss about the protection of the Thyristor. So let us discuss what are the different types of protection methods, how we can protect from the different abnormalities of the source side as well as the load side, right? For that, let me introduce myself. This is the present offer is going on, so up to which it will end at 31st. End at 31st October. The offer alert. This is for GATE and ESE. Subscribe for the 4 months, you will get the additional 1 month. Here, if you subscribe for the 4 months, you will get additional 1 month. From there, you can save the 6,300 rupees. Right? Let me introduce myself. I am Sathish Kumar Kesireddi. I got AR 18 and AR 286. I had a 10+ years of teaching experience. I did my MTech Power Electronics from NIT Tirchi. I was ex-BHL employee. So I was expertise in the subjects of power electronics, power systems and network theory. If you use the code as KSK10, you will get the 10% discount. Right? In Unacademy, we have the 2 types of subscriptions. So one is plus subscription, other one is iconic subscription. Right? In a plus subscription, we have the live classes, as courses will be there, tests will be conducted, doubt solving sessions also there. The classes will be held in English and Hindi. Rank improvement batch is also there in case of the plus subscription. In case of iconic subscription, right? So you are allotted with the personal coach. The study planner sessions will be there. Study booster sessions will be there. Personalized test analysis will be there. Dedicated doubt clearing instructors will be available. Preparatory study material is also available in case of iconic subscription. Plus subscription for the 12 months, 18 months and 24 months subscription. Here you can opt for the no cost EMI. Here you can opt for the no cost EMI, right? So from there you get the monthly amount of this one. Right, this is the iconic subscription. For iconic subscription, this is for 12 months, 18 months and 24 months. 12 months, 18 months and 24 months. So these are all the amounts for the 12 months, 18 months and 24 months. Here you can opt for the no cost EMI. Unacademy Ask a Doubt, which is a new initiative, right? So ask unlimited doubts, ask doubts at any time, get high quality video solutions, both English and Hindi, right? Live mentoring product will be there, which is for the 1:1 live mentoring will be available from the iconic subscription. Web batch for the GATE 2023. So gate 2023, this is for electrical. The classes will be held in English. This is your batch for the gate 2023. The class will be held in English. This is for ECE. So this is RIP batch for the gate 2022. So this is bilingual. The classes for electrical branch. The starting date will be the 20th October 2020. So these are last 10 years of gate papers will be here. Question papers will be placed here. Right? To unlock this one, use the code KSKTEL. So this is my username. Right, this is my username. Follow my username, you will get the notification. Good afternoon. Good afternoon. Try to share the session. So try to share the session. Mahesh, good afternoon. Try to share the session, guys. So Drupad Saha, good afternoon. So try to share the session. Try to share the session. Try to share the session, guys. So in this session, let us discuss about the protection, why we need a protection. So to protect the SCR, what are all the different elements are required? What are all the different circuits are required, right? So how we can protect the SCR from the different abnormalities. So let us discuss everything here. Let us discuss everything. Let me start with the question. So when will be the, here let us see the protection of SCR. So protection of SCR, why we need a protection? So can anyone tell why we need a protection here? Why we need a protection in case of SCR? Why we need it? Why we need the protection in case of SCR? Anyone tell? So as we know that SCR has a turn on and turn off instance. The SCR can be turned on. SCR can be turned on when it is forward bias condition. So when it is forward bias condition, if you supply the gate pulse to the SCR, when latching current, when anode current is more than the latching current, it will get turned on, right? When it will be turned off, the SCR can be turned off. SCR can be turned off when the anode current equal to 0 or anode current is less than holding current. The reverse voltage must be applied certain period of the time, and that period it is called as circuit turn off time, and this circuit turn off time should be greater than the device turn off time, right? So this is the basic SCR turn on and turn off condition. Now tell me why the protection is required. Why the protection is required? Why protection is required? On what parameters this protection is required? Now let me represent SCR with the switch. Now let me represent SCR with the switch. So now one more question, why the snubber circuit will be? Can anyone tell what is the purpose of snubber circuit? So as we have seen that different cases, in different competitive exams we have seen that what is the function of snubber circuit? What is the function of snubber circuit? What is the function of snubber circuit? Even tell what is the function of snubber circuit? Subhad, right? So it is for dV by dt protection, right? So it is for, generally we know that, so in most of the competitive exams also this question will come, right? So the SCR, the dV by dt, the snubber circuit will be used for the dV by dt protection. Is that only, the snubber circuit is designed for only that purpose? Is the snubber circuit is designed for only that purpose? No. So it has different purposes in the protection of the SCR. Let us investigate all of those. Let us investigate all of those. Here, let me start from the basics. Let me start from the basics. So let me take the SCR is a simple switch. SCR is a simple switch. Let me assume that SCR is, as we know that SCR contains anode, cathode and gate terminals. Anode, cathode and gate terminals. So let me replace this as a simple switch. Let may replace with the simple switch, right? So if I take the simple switch, the voltage across switch will be the VSW and the current flowing through the switch equal to ISW. Let us assume that voltage across switch equal to VSW and the current flowing through the switch equal to ISW. If I draw the switching characteristics, how the switching characteristics will be? If I take the practical switch, what happens during the turn on and turn off? Let me draw the switching characteristics for the practical switch. If I draw the practical switch, so what is the turn on and turn off characteristics? Let me draw the turn on and turn off characteristics so that you will understand clearly. I have taken the SCR and represented with a simple practical switch. I have represented with the simple practical switch. Now I am going to draw the turn on and turn off characteristics or the dynamic characteristics of SCR. In ideal case, with some assumption, if you draw that, so it will be like this. So if I take the voltage across the switch, if I draw the voltage across switch, so let us assume that the steady state value of the Vs will be like this. Steady state value of the Vs will be like this. During off condition of the switch, it is Vs. So let us assume that from here to here the device is going to be turn on. So the turn on time of the device will be from here to here. So Vs will, during on condition of the switch, what happens? The Vs will be reduces. Let us assume that device drop is 0 here. Right? What about the current? The current will increases. To steady state. If I draw the current will increase to steady state. What happens after that? So it will maintain the constant current, that is Is, during the turn off time. After turn on delay, what happens? Maintains the constant current, output voltage will be like that. Now what about the voltage here? During the turn off process? Now I have initiated the turn off process here. Now what happens during this time? So let me call this as a TR, that is turn on time of the switch. Now, so here the source current will reduces to 0. It takes some time, right? Because it is a practical switch, it takes some time, and the voltage will be like this. Right? Let me make it as a TF. This is the off transition of the switch. Now tell me, the losses is more in which case? Now tell me, which case the losses are more? Here the three different cases you can observe this. We have drawn the basic switch characteristics here. S is connected to the power circuit. Not like that. Just observe here. Let us learn the basics first. After that we will connect these basics to the circuit. Now, so in which case the losses will be more? If I find the losses here, let me take this as the on transition time, and this is the off transition time. And here the voltage is maintaining constant. We find in ideal case, it is having the minimum initial current, so it has some conduction losses, that is minimum conduction losses will be. So the losses will be here. So the losses during the transition is more than the losses of the device. During transition is more than the losses during the conduction period and blocking period. Losses during the conduction period. Let's assume that this is right. What we have seen here. So from the basic point we have observed that. So if you observe here, what is happening here? So the voltage is increasing here, the current is increasing, and the voltage is decreasing. If I find the power losses, for this, how the power losses would be? So in this case, the power losses, the switching losses will be like this. So here, if I draw the switching losses will be like this. So here, if you assume that the device voltage drop equal to 0, which is very less, even if I take it is less than during the transition period. The power losses during the transition period is more because of the high current and high voltage. So during transition it will be more because of the high current and high voltage during the transition period. During the transition. Suraj, good afternoon. Try to understand the basics first. What we have understood from this. So basic point, very basic point, but it is very important. So I have taken the switch. That is SCR. SCR, any device which is in the power electronic devices, so which we can replace with the switch, right? Now I have replaced with the switch. Now, so for the practical switch, I have drawn the characteristics. From these characteristics, what we have observed. So here, during the transition time of the switch, if I find the power loss, the power loss will be more. During the conduction period as well as the blocking period, the losses will be less. Either voltage or current will be less in case of the conduction period and the blocking period. Now again, if you take the off transition, what happens? So here also the power losses will be more. I think it is clear. Losses during the transition because of the high voltage and high current is more than the losses during the conduction period and blocking period. It was clear. Because it has a high current and high voltage. Now, to reduce the losses, what we have to do? We have to reduce the so this TR, we have to reduce the TR and TF, right? TR and TF. What is the TR? So this is the on time delay, on delay time. So TF is the off delay time. We can reduce, and we can reduce the current and voltage. By making this, so we can reduce the current and we can reduce the power losses, right? Now, what are the reasons why we need to reduce the current and voltage? Is to reduce the losses only. So why we need to reduce the current and voltage during the transition? Here? For example, if I take the safe operating area, what is safe operating area? Can anyone tell what is safe operating area? What is safe operating area of the device? What it specifies? What is safe operating area of the device? So, the safe operating area of the device is nothing but, for example, if I take a transistor, the safe operating area is in the first quadrant, right? The safe operating area will exist in the first quadrant. So, if I draw the safe operating area of the transistor, so what happens? So, it will be the, if I drag the V, so it will be the Vmax. If I take the IV curve, so it will be the Vmax. The maximum rating will be like this for the transistor. So it will be the power loss, that is Pmax, specifies the Pmax, right? If you take the transistor, there exists a secondary breakdown. That is temperature limit, right? So and there, so we have the current bank. So now, to make the device operating into the safe operating area, so for every device there is operating constraints. So what are those operating constraints? For example, if I take the voltage, so it has to be operate within the less than the maximum voltage. For example, if I take the power, it has to operate less than maximum power. If I take the temperature limit, it has to operate, the specified limit will be mentioned, that is maximum temperature limit, so it should operate before the temperature. To make the device into safe operating area of the device, if it exceeds the safe operating area of the device, what happens? The device can be damaged. So it should operate in the safe operating area. So the devising area with the optimal performance. Very good. Now, on what parameters? First, we have seen the losses. The losses can be reduced like this. On what parameters it will depend? On remaining parameters, what parameters it will? So it will depend on dV by dt, we need to keep the dV by dt and di by dt in specified limits. dV by dt and di by dt in the specified limit. Specified limit. dV by dt and di by dt in the specified limit. So to operate the device in a proper, so in a safest way, what we need to do, we need to operate the SCR. We need to operate the SCR in such a way that the dV by dt maximum, that is sudden voltage applied for a small period of the time. So if it is high, so it will be the dV by dt. Similarly, di by dt, the sudden voltage applied in a short period of time, so will make the more current flowing through the device, more voltage across the switch. So if the dV by dt is more, what happens in case of SCR? So it should be in the specified limit. First, the losses should be minimum, so that we need to keep the current and voltage as well as TR and TF will be minimum, right? The second is the safe operating device. We need to ensure that the safe operating device has to be a safe operating device. So the device should be operated in the safe operating area. So the third one is, what I have mentioned here. So the dV by dt and di by dt are in the specified limit. dV by dt and di by dt are in the specified limit. For example, if the dV by dt level exceeds, what happens? If the dV by dt of the device, that is sudden application of the voltage with shortest time, is greater than the device maximum, what happens? The maximum rate of device, so what happens? Can anyone tell what is the reason? What happens if the dV by dt exceeds its limits? So see in the safe operating area, if it exceeds the safe operating area, the device can damage. The device will damage. So now, what happens if the dV by dt exceeds the limits? dV by dt exceeds the limits. If the dV by dt, that is sudden voltage applied across the device, exceeds its limits, what happens? So there will be the false triggering happens in case of the false triggering happens. False triggering will happen. What is false triggering? So we have seen in the firing methods, that is triggering methods of SCR. In triggering methods of SCR, so as we have seen that, so it is proportional to the VC, the voltage across the device junction is proportional to the capacitance into dV by dt. So we have seen that. So if I take the junction capacitance here, that is the junction J2. Let me draw the junction J2 because it is in the reverse bias condition, right? C is J2 into dV by dt, right? Which is equal to IC. That is junction current. The dV by dt exceeds its limits. What happens? So unwantedly the device will get into the turn on, which is called as false triggering of the device. So which is called as false triggering of the device. So which allows the high current through the device, so it's called as false triggering of the device. What happens to the di by dt? di by dt exceeds its limits. What happens if di by dt exceeds its limits? What happens if the di by dt exceeds its limits? If the di by dt exceeds its limits, what happens? So the current crowding will be happens. The current crowding phenomena will happen. So the current crowding phenomena, so the sudden high current will causes the hot spots across the junction, so which will damage the device. So that we should ensure that we must ensure that the dV by dt and di by dt should be less than its limit, right? The hot spots will be happen if the di by dt sudden high current is applied across the device. What happens? It will be like this. Now let us see the next. So the temperature limit should be maintained. How the temperature limit should be maintained? So on what parameter the temperature will be depends. For example, during transition condition here, if you observe during the transition condition, what happens? During the transition condition, if the device is approaching to the energy losses, the device will get the energy loss or the power loss. The device will cause the more power loss, and these losses will be dissipated. These losses will cause the heat in the device, will cause the increase in temperature in the device. So the increase in temperature, so if the increase in temperature exceeds its maximum temperature, the device will get damaged. what happens? The energy losses are more. The energy losses are more, or the power loss are more. So what happens here? The power loss is more. If the power loss is more, which causes in a number of cycle number of times if the transition happens, so what happens? If you find the total power loss in a cycle, the power loss will be more. If the power loss is more, what happens? So the temperature exceeds. The temperature more, the temperature exceeds the temperature limit, it will damage the device. It will damage the device, right? Now last one. Let us see the last one. Now, in some applications, what we will do? We will connect the diode across the switch. We will connect the diode across the switch. That is anti-parallel across the switch. So, for example, if you take in case of inverter, what happens in case of inverters? So, in case of inverters, for non-unity power factor loads, there should be reversal of current is needed. For that purpose, generally we will keep this diode in the reverse condition. What happens during the on time of this switch? So for the diode, we have the two times, that is forward recovery time and the reverse recovery time. The forward recovery time is related to the turn-on process of the diode. The reverse recovery time is related to the turn-off process of the diode. Indirectly, for example, if the T1, the diode has to be turned off at 5. It needs to be turned off at 5. Assume that diode has to be turned off at 5. Because of the reverse recovery time, assume that it is turned off at some other value. So, for example, it is 10 milliseconds. Assume that it is at 10 milliseconds. It has turned off at 12 milliseconds. What happens during that condition? It will directly affect, during that time, it will reverse bias the thyristor. The thyristor will be in the off condition. Even if I want to on, so the thyristor will not turn on. Directly, what parameter it will affect? It will affect on the turn-on time of the device. Because of the reverse recovery time and the forward recovery time of the diode, so what happens? It will affect the turn-on time of the device. So that we need to avoid this one, that is, we need to have the low recovery time and as well as the low forward recovery time, so that the device does not affect the device much, right? Now let us understand. Let me summarize all this. From the starting point onwards, why we require a protection here. The first point is, if I am unable to protect the circuit, so definitely if the protection circuit is not there, so the protection circuit has a different functions, not only the dV by dt protection, which has a different functions, like it will reduce the losses. During the transition time. How it will, we'll see further. We'll see in the next slide. So how it will be? It will reduce the losses, and the protection circuit will ensure that the device will operate in the safe operating region. That is, it should operate in the maximum voltage limit, it should operate in the maximum current limit, it should be operate in the maximum power limit, it should be operate in the maximum temperature limit. That is, operate in the safe operating area of the device. The third point is, so the dV by dt and di by dt should be in the, because if the dV by dt causes the false triggering of the device and di by dt causes the current crowding in the device, so they should be less, so within the limits. So the protection circuit should have function like that. These two should be within the limit. One third one is energy losses, that is power losses during the turn on and turn off causes. If this period is more, so for example, if I find the power loss here, so we have already derived. So E on equal to energy loss equal to, during on state it will be the Vs into Is into T on by 6. Right? So it is depends on the T on, it is depends on the Vs, and it is depends on the Is. Right? If I can able to reduce the voltage value and current value and time, the losses will be reduced. All these parameters. it will affect the turn on time of the device. It will affect the turn on time of the device as well as turn off time of the device. Now, the last one what we have seen. When the circuit will operate like this, so whatever be the parallel device which was connected, so the device characteristics will affect the turn on and turn off time of the switch, which is also causes additional energy losses in the system, right? So now, what we have to do? Right? So to make all this possible, so what I have to do? So I need to keep an additional component. I need to connect the additional components in such a way that so it should perform that. It should fulfill all the reasons. So how it will fulfill? So let us see how it will fulfill. So for example, we need to connect the additional elements. That circuit is called as snubber circuit. Let us see the snubber circuit now. The circuit is called as snubber. So to fulfill all the conditions, we need an additional element that should be connected to the. We need an additional element that should be connected to the SCR, right? We need an additional element that should be connected to the SCR, and these all are connected. So all that additional components which can make the circuit, and that circuit is called as snubber circuit. So now, if anyone is asked for the function of this snubber circuit, so not only the dV by dt and di by dt. It is not only the dV by dt and di by dt. It has different functions. It should fulfill all the components. It should fulfill all these things. Now, this snubber circuit is classified into two types. So the first one is turn on snubber circuit. Turn on snubber circuit. Right? And the second one is turn off snubber circuit. Turn off snubber circuit. What is the turn on snubber circuit and what is the turn off snubber circuit? What is the function? To improve the performance parameters, that is T on, losses, and all energy losses. So for that, so we need to use the during turn off process, during the off transition, if you use that circuit, which is called as turn off snubber. So if you use for the turn on condition, during the turn on condition, if I use, so it will be for the turn on snubber. Now let us see what is the turn off snubber and what is the basic turn off snubber we can implement. Let us see. So here, what is the switch here? Let me take the switch here. So assume that initially it is an on condition. The switch is initially on condition, right? So now, what is the turn off snubber? Why the turn off snubber is needed? At the basic level, let us see. So at the basic level, if you observe that the switch is connected like this, at t equals 0, let us assume that at t equals 0, the switch is in on condition. At t equals 0 plus, if I open the switch, what happens? For example, if the inductive load is connected across the switch, the load is an inductive nature. For this switch, let us assume that it is connected to the inductive load, or else the spray inductances are connected across the switch. So which causes what happens here? So here, if I open the switch, so initially the inductor is flowing, inductor is allowing during the turn on state, the inductor is allowing some current, which is, let us assume that which is IS. Now, if I open the switch, what happens here? If I open the switch, this IS has to be 0. Now, if I find the voltage across inductance, PL equal to LDI by dt. Now, what happens here? PL equal to LDI by dt. So, during the short span of the time, during the zero time, within microseconds, this current is 0. That is IS divided by, during the 0 time, what happens? It causes high voltage inductance, that is destructive voltage across the switch, which causes high voltage across the switch, which can damage the switch. So to eliminate that one, so here in case of basic turn off snubber, we will connect the capacitor. Right? We will connect the capacitance here. Why we have connected the capacitance? Try to observe the concept. So when the switch is connected to the inductive load, or the stray inductance. When it is connected to the stray inductance, what happens? So when it is connected to the stray inductance, or when it is connected to the switching network, what happens here? So when suddenly if the switch is in open condition, what happens during that time? So the high voltage will appear across the switch, so which can damage the switch. So that we will connect the capacitance across the switch. In case of turn-off snubber, to avoid the destructive voltage across the switch because of the inductance, so here we will connect the capacitor. Right? We will connect the capacitor. Now, so what is the condition for the turn-on? So let us assume that. Initially the switch is in open condition. So here, if I close the switch, at t equals 0, it is an open condition. If I close the switch at t equals 0 plus, what happens? If I close the switch at t equals 0 plus, what happens? So here, let us assume that it is connected to the capacitive load, or it is connected to the stray capacitor. So assume that the switch is connected to the load as a capacitor. What happens there? During that condition? So this initially the switch having some voltage. The voltage across switch, when switch is in open condition, whatever be the blocking voltage, it will appear across this. So if the voltage is suddenly 0, so I equal to C into dV by dt. Right? C into dV by dt. If voltage is suddenly changing with respect to time, with respect to 0 time, what it causes? It causes high current flowing to the switch, which can damage the switch. Now, for the turn-on snubber, what we have to do? For the turn-on snubber, I need to connect an inductance in series with the switch to avoid the high current flowing, that is destructive current flowing across the switch, which can damage the, right? Now let us see the basic turn-off snubber circuit. Let us analyze the basic turn-off circuit, how it will work. Let us analyze the basic turn-off circuit. Basic turn-off snubber circuit. Let us analyze the basic turn-off snubber circuit. As we discussed earlier, so initially the switch will be like this. Let us take two conditions here. Initially the switch is like this. So we have not connected any snubber element here. But when it is connected to the load, when it is connected to the inductance, what happens? I think you have understood. Are you clear with this? So when you connect to the inductance, what happens here? Try to tell me, guys. When you connect to the inductance, what happens? When you connect to the inductance, what happens? Up to here you are clear, right? So try to respond, guys. Up to here you are clear. When you connect the inductance, if you are clear, tell me the answer, guys. When you connect the inductance, what happens? You connect the inductance as a load for this switch. What happens? Because of the inductance, there is a chances of getting the high voltage across the switch, so which can damage the device. So that what we are doing, we are keeping the capacitance across the device. Let me keep the capacitance across the device. What it can do? So here, the capacitance property is it doesn't allow the sudden change in the voltage, so it can limit the dV by dt. That we can tell that. It can limit the dV by dt. But is this only function for the turn-off snubber? There are different functions are there for the snubber circuit. Let us investigate all those functions. Let me take this as a case 1. Here we have the two cases, case 1 and case 2. In the case 1, let me draw the switching characteristics for the case 1. Let me draw the switching characteristics for the case 1. How I can draw? Let us see. For the case 1 and case 2, let me draw the switching characteristics. so that you will understand all the concepts. Right? Yes, high voltage appears across the switch. Very good. High voltage will appear across the switch. Now, let us investigate. Let us see how it will. If I draw the voltage across the switch and the current flowing through the switch for the case one, during the turn off state. Let me draw for the only turn off state. How it would be? So before that, let us assume that before that it is in the turn on state. So the current will exist, right? So at this instant, if I want to make the turn off the device, turn off the device at this instant, what happens? The current will reduces to zero. The current will reduces to zero like this. Right? The current will reduces to zero like this. Now, what happens? The voltage will increase. The voltage will increase. At this portion, it is to. As I assume that at this portion, it will increase to. Right? This will be called as, we are called as TF. This period we are called as Now, let us assume that, let us draw for this second case, VSW and ISW. Right? VSW and ISW. Initially assume that the device is on condition, that the IS is. Now we have initiated the turn off process here. What happens here? So now let me explain you what is happening. So here, at this portion, what happens here? If I take the voltage across capacitance, so let me draw the current flowing to the capacitance. If I am assuming that the total current, here that current will be, let us assume it is the I0 current. So let us assume that the switch current equal to ISW, and the capacitor current equal to IC. Let me assume these three currents. What happens here? You observe here. So the switch current, if I find the switch current, what happens? If I find the switch current, is equal to I0 minus IC. Find the switch current within. Before that, so we have assumed that this I0 will be constant. So let us take it as IS. So let me call this the IS minus IC. Now what happens? The capacitor slowly charges. So capacitor is trying to charge. Right? So at particular portion, because IC is increasing, so that IC also increasing. So during that time, what about the switch current? The switch current minus IC, so ISW reduces. So which makes the device into. So here, actually here the device is turned off here in the first case. Now the current will be zero before the TF. Let me call this as a TF. Right? Because of the capacitance here, the voltage will increase slowly. And somewhere it will reach. Let us assume that somewhere it is reached. And this slope depends on the 1 by C. So this slope depends on 1 by C. That is capacitance. It is indirectly proportional to the capacitance. So try to observe this one. What is happening? So the TF dash has reduced. The turn off losses, if I find the turn off losses, here if I draw the turn off losses, the turn off losses will be like this. Right? If I draw the turn off losses here, the losses will be like this. So try to understand. Just you need to keep a minimum concepts here. To understand the minimum concept, that is sufficient. Here there will be some approximations are there, but try to understand the concept here. If I take the VC equal to dV by dt, so IC equal to C into dV by dt, right? So what is the voltage here? So voltage equal to 1 by C into integration of IC dt, right? So it will depends on slope. If IC is assumed as, let us assume that IC will be assumed as a constant value, so with the slope will be depends on I by C. Slope will be depends on IC by And if I choose the more value of C, if I choose the more value of the C, what happens? The slope will be reduced. It will take more time to reach B. It will take more time to reach the B. If I increase the C value, it will be like. Now, here you need to observe the two cases here. You need to observe the two cases here. What are the two cases? Here, if you observe that, assume that this is a linear. So here, take some approximation, a linear to understand this circuit. So here, what happens here? What we need to observe here? The TF has reduced. The TF has reduced. So the TF has reduced. That is, off time, delay time is reduced because the current is 0 here itself. Current is 0 here itself. And the voltage during that time, so which is reduces, and it is depends on C value. Let us assume that this is reduced by the fraction of the K into Vs, K into Vs. Now, if I find the power loss, that is Vs into Is into T off by 6, the power loss here, energy loss here. So here, if I find here, if I take this is also linear. So here it will be the Vs, that is K into Vs into Is to Tf dash divided by 6. Tf dash divided by 6. So now, if you find the power loss, so what happens? Find the power loss. What happens? Not only it is doing the dV by dt, it is also reducing the losses. Losses of the switch and the voltage across the switch. So power loss across the switch, that is switching loss across the switch, and it is also affecting the TF also. That is off time, delay time also it is affecting, right? So delay off time also. In case of 1, voltage is not sudden. In case of 2, voltage is not sudden. How it reduces? High voltage is not suddenly changed. So let us understand. Here, if you take inductance is there, assume that so there will be the inductive load, inductance load, or the spray inductance due to the circuit. The circuit, there will be the spray inductance. Assume that there will be spray inductance, or the inductive load is connected. Assume that this switch is connected to the inductive load. What happens there? If the switch is in off condition, initially it is in on condition, there is no problem. It is carrying the current of Is. When switch is in off condition, what it has to do? So the current should be 0. So because of that, there will be high voltage will appears across the switch. High voltage will appear across. So let us assume that here also load is connected as an inductive load. Load is connected as inductive load. Don't assume that it is directly, it is not connected. We are not intentionally connected this inductance. This is because of the load or the stray inductance, right? This is the inductance, we are not connected intentionally. This is because of the load circuit. This is because of the load circuit as well as circuit topology. So because of this also, here voltage will be induced. But this capacitance, what it will does, the capacitance voltage will be slowly increasing. The capacitance voltage will be slowly increasing. So the capacitance voltage equals switch voltage here. In this case, the capacitance voltage equals switch voltage. We can find from that. We can find the capacitance voltage equal to switch voltage. So because of that, here the voltage will be applied slowly. Even though if I applied so sudden voltage, what happens here? So because of the capacitance, applying slowly. So due to that, what happens? The TF has reduced and the dV by dt also reduced. So the dV by dt also reduced. Right? The slope will be reduced. If I choose the large value of the capacitance, the slope will be reduced. If I choose the large value of the capacitance, the slope will be reduced. I think up to here we are clear. Is there any doubt? Is there any doubt? Is there any doubt? Up to here we are clear. Is there any doubt? If you have doubt, you can ask, guys. If you have doubt, you can ask. No need to understand. No need to get. So try to ask the doubt. Whatever be the doubts you have, you can ask. So the dV by dt will definitely reduces because we have connected the capacitance. Because we have connected the capacitance, if I choose the large value of the capacitance voltage will increase slowly. Capacitance. If I choose the large value of the capacitance, what happens? The slope will reduces. The capacitance will take more time to reach the Vs. Will take more time to reach the Vs. So that what happens here? it will make the dV by dt is less. If I choose the capacitance value is more, so what happens? The dV by dt will be less. The slope will be less, right? The dV by dt will be less. So if I choose the capacitance in such a manner that what happens? The capacitive current increases, because before that, so the switch current is equal to load current. Now here the switch current is load current minus capacitor current. As the capacitance charges slowly, the IC also increases, which makes the switch current equal to 0 before the TF. Makes the switch current into 0 before the C. Right? Up to here we have understood, right? Now how can we find the C value? So this is the turn off snubber circuit. How can we find the C value? Let us find the C value. How can we find the C value? So now let us take, this is the TF dash. This period will be the TF dash. Let us take this period will be the TF dash, and this where this voltage is becomes 0. So this will be K into Vs. Let us assume that this is the K into Vs. Now if I find the I naught equal to, so I switch equal to, so what is the current here? So I switch equal to I naught minus IC. That is IS minus IC. If you assume that it is IS, so it is equal to IS minus IC. How can we find the IC? So IC equal to C into dV by dt we can find. How can we find the IC? So try to find the C value. If you have any doubt till now, you can ask, guys. If you have any doubt till now, you can ask. So otherwise we will continue here. If you have any doubt, you can ask. Otherwise we will continue. Right? So let us find the IC from this. IC equal to IS minus IC equal to IS minus ISW. So what is ISW? It is decreasing linearly. Right? Which is decreasing linearly. ISW will be like this. Let me draw the ISW with yellow color. So the ISW now it will be like this. This bit will be the TF dash. Now try to find that. This bit will be the TF dash. So now try to find this. So ISW equal to, this height is IS and it is decreasing linearly at 0, at TF in this period it is 0. So it is a decreasing slope. If I write the line equation, how it would be? IS into 1 minus T by TF. That's IS into 1 minus T by. So now IC equal to C into dV by dt. IC equal to C into dV by dt. If I substitute this, so try to find the capacitor value. How can I find the capacitance value here? So the capacitance value here, how can I find here the capacitance value? So IS will get cancelled out. It is equal to IS into T by TF. Right? So IC equal to C into dV by dt. Right? Let us assume that it is varying from 0 to Vs, 0 to K into Vs. Let us assume that this is also linear. The dV will be the K into Vs, 0 to K into Vs. It is varying at this point, it will be the Vs, K into Vs. This point will be the, so K into Vs divided by T. So that is TF. So let us find this. C equal to, so dV equal to C equal to IS into T divided by T5, T divided by TF into dt. E into CV, E into dV to dt. If I take this as a limit, so if I integrate in between the 0 to TF, what happens? It will be the T square by 2. The substitute will be the TF divided by 2. IS into TF divided by 2. So here it will be the C into V. C into Vs. So this potential will be the, let us assume that this potential will be K into Vs. So now if I find the C, it will be the Is into Tf divided by 2 into Vs into. This is how we will find the C value. We can design the C value from this. Try to observe this waveform. If you are still confusing, let me draw the voltage waveform here. Vs and ISW, you can understand it. If I take the VSW and ISW here, so VSW and ISW here, how it would be? Initially it is Is, at Tf it becomes to 0, at Tf it becomes to 0, Is. So the voltage will be start from here, it will reach us to the K into Vs. Let us assume that this point will be the K into Vs, right? So K is the fractional value and it is somewhere it is reaches to the Vs, and this will be the Tf dash. So from this we have determined, as we know that Ic equal to Is minus ISW. So Is is assumed as which is a constant value, that is load current, equal to, if I take the slope, that is steady state value, if I take this slope, what is the ISW? So ISW equal to Is into 1 minus T by Tf. So this line equation will be the Is into 1 minus T by Tf, that is y equal to mx plus c, you can apply. So from this, if you find this, which is the Is into T by Tf, right? So what is the value of the voltage here? The voltage is varying from the 0 to Vs. But if I take the dB here, it can vary from the 0 to K into Vs, and the time is varying from the 0 to Tf. If I substitute that, I will get the C value. So get the C value, right? This is the turn-off snub. This is the value of the turn-off snub, right? So if I take the practical snubber circuit, it will be different. So why it will be different? Let us see. If I take the practical circuit, let me draw the practical circuit also. The practical turn-off snubber circuit. We have drawn the basic snubber circuit. If I draw the practical turn-off snubber circuit, let us see how it would. If I draw the practical turn-off snubber circuit, how it would be. So why we have to go for the practical turn-off snubber circuit? Let us see. So now, Rupasaha, right? If I take the practical turn-off snubber circuit, so practical turn-off snubber circuit, it will be like this. If I take the practical turn-off snubber circuit, if I take the capacitance here, so what happens? Now, let us understand the practical turn-off snubber circuit. So this is the theoretical, that is basic turn-off snubber circuit that we have derived. Is there any disadvantage in this? Why we have to, when it is going to the practical, what are the parameters we need to change? Try to understand. So is there any disadvantage in this? In case of the turn-off snubber circuit, is there any disadvantage in this? So why we have kept this initially? Because of during the off condition it will be like this. So if I draw the VA characteristics, what happens? If I draw the VA characteristics, what happens? The voltage across the current flowing the switch equal to somewhere at Tf dash it is equal to 0, right? So the voltage will be start from here and it will increase, right? And it will reach us to the Vs somewhere at here, and it is depends on the slope of the capacitor. It will depends on the capacitance value. Right? This is the ISW and VSW. What is the disadvantage here? Can anyone tell what is the disadvantage here? For example, after attaining the Vs value, now I want to turn on the device. What happens if I turn on the device? What happens if I turn on the device? Yes, capacitor size of the capacitor. The rating of the capacitor will be depends on, so Tf, and it will be rating of the capacitance can be determined like this for the turn-off snubber circuit. What happens? This is not the size of the capacitance. It is not about size of the capacitance. Is there any disadvantage is there? Now the turn off process has completed. The turn off process is completed like this. Now the capacity is charged to the Vs, that is plus minus Vs. Assume that it is charged to the Vs. Now if I turn on the capacitor, if I turn on the switch, now I want to turn on the switch. The turn off process is completed, that is one cycle is completed. In the next cycle I want to turn on the switch again. So what happens? Next cycle, if I want to turn on this device, what happens? Next cycle, if I want to turn on the device, what happens? Here I want to turn on the device. Here I want to turn on the device. So what happens? Can anyone tell? Try to answer, guys. Try to answer. Losses is not reduced. Losses is not reduced. Not like that. Not like that. Because the turn-off process is already completed. In the turn-off process, we have already reduced the losses during the turn-off process. If I draw the losses here, the losses will be from here to here. Right? The losses will be here. So the losses is reduced when compared to the previous case. The losses also reduces, TF also reduces, dV by dt also reduces. But now I have placed this practical theoretical snubber circuit, that is basic turn-off snubber circuit, in a practical case. In a practical case, as you know that, so here the pulses should be in the periodic nature. The pulses are in the periodic nature. Again it will start at 2 pi plus alpha or something, right? So again it will start at t plus alpha. For every period it has to be turned on here. Now the device is turned on here. After attaining the Vs value, that is capacity charged to the plus minus, now at this position the capacity charged to the plus minus Vs. Now I have turned on the switch. If I turn on the SCR, what happens? Now if I turn on the SCR, what happens? Switching delay will be there. Delay will be there. Let us see. Let us see what happens. Let us see. If I turn on the switch, the load current flows in this. The load current flows in this circuit, right? In addition to that, the capacitor is shorted here. What happens? This capacitor is also trying to discharge its current, discharge its energy through the switch. So that what happens there? So the capacitor, the switch will carry the current of, load current as well as capacitor current. Load current as well as capacitor current. Load current as well as capacitor current. What happens if it is carrying the more current here? If the capacitor current is more at this time, because it is a Vs, what happens during that time? So there is more losses, as well as there is a possibility to damage the switch also. There is a possibility of destruction of the switch as well as there is a possibility of increase in losses, which can cause the increase in temperature, and everything will be happens. So everything will follow right. Now, so the capacitor will discharge if I keep like this. Now I need to limit the capacitor current. So how can I limit the capacitor current? I need to place the resistance. Right? I need to place the resistance. Now what happens? Yes, very good. It carries the maximum current, it will damage the switch. Clear, very good. Your understanding means it was very good. That slowly we are going into the concept. So you will understand, everything you will understand, no problem. Now let us see. Is there any disadvantage in this circuit? Is there any disadvantage in the circuit? Still, is there any disadvantage in the circuit? Still, is there any disadvantage in the circuit? So understand the basics. Yes, resistor with the capacitor will limit the discharge current. What is this function of the resistance? What is the function of this resistance? It will discharge as the current. So it will limit the discharge current. Right? Now tell me, guys. So it is limiting the discharge current. Clear? It is limiting the discharge current. Is there any disadvantage? Still, is there any disadvantage in this circuit? Still, any modification is required here. Now understand this. Still, any modification is required, right? So, and understand. Now, so it has turn on process completed. Assume that The turn on process has completed here. The turn on process has completed here. Again I need to turn off. Again I need to turn off. So what is the time constant now? What is the time constant now? So now the current flows, the capacitor current flows through the RC circuit. Now the capacitor flows through the RC circuit. To the RC circuit. So which causes additional losses, right? Which causes additional losses. What happens during that time? Causes additional losses, as well as it will depends on time constant RC. The time constant will be different. What I have to take? What I have to take? So if I place the diode here across the resistance, if I place the diode across the resistance, what happens? If I place the diode across the resistance, what happens? If I place the diode across the resistance during the turn off state, directly the capacitance will be available at the switch, because the diode will be in the forward bias condition during the turn off state of the switch. So the diode will be in the forward bias condition. So directly the capacitance voltage will applying across, the capacitance will divide the high dV by dt, right? So otherwise the capacitor has to be charged with the R and C side. RC side. In the charging side, so during the charging, so it doesn't require the R value, so that we need to take off that R value during the charging, and we need to have the R value during the discharging current, so that during the discharging time it has to limit the current. Now if I draw the total circuit of the turn off snubber circuit, how it would? If I draw the total turn off snubber circuit with the SCR, let me draw with a different color. With the SCR, how it would? If I take the SCR, right? So across SCR, if I kept the capacitance, we have the RS value and kept the capacitance, right? So we have kept the diode also here. And this diode should be forward bias only during the forward bias condition. Diode will be in this. Let me call this as a R and this C and RC. This is the complete turn off snubber circuit. Complete turn off snubber circuit. Turn off snubber circuit. Turn off snubber circuit. Right. Now, is there any change in your statement? At the starting of the lecture, I asked the question, what is the purpose of snubber circuit? So what you have answered? So the snubber circuit purpose is, what is the function of snubber circuit? The purpose of snubber circuit is to reduce the dV by dt value. Reduce the dV by dt. Now tell me, what is the function of the snubber circuit here? At this stage, what is the function of snubber circuit? How diode limited current? Or can you please tell operation statement? Let me tell. So diode does not limit the current. R only limit the current. The resistance only limit the current. So the diode does not limit the current. But if I need the capacitance during the turn off state, I need the capacitance to eliminate the high dV by dt. For example, during that state, if the resistance is there, what happens if the resistance is there? So the voltage across the switch, which is equal to voltage across the switch during off condition of the switch, which is equal to PR plus VC. Right? So, but the magnitude it should be designed for the maximum dV by dt, and during this condition, this resistance should not be worked. During the charging of this circuit, during the charging of this capacitance, the resistance is not required. So the capacitance has to be it should depends on capacitance. It must depends on capacitance. So, but when I close the switch during that time, so that's why I have kept the diode here. If I kept the diode here, what happens? So the diode, when the diode is in on condition, so this resistance function will be not considered, because when it is short circuit across the resistance will make the, so it will make the short circuit across this one, so that only capacitance will be there in case of the charging time, But Now I want to turn on the switch. Now capacity charged to the Vs and it is turned off, but now I want to turn on the switch. Now if I want to turn on the switch, so what is the capacitance polarity? The capacitance polarity will be minus, plus and minus, right? Here the resistance is there, so here the resistance is there, and the diode is also there. What happens during that time? Plus is connected to the cathode of the diode, so which makes the diode into off condition, which makes the resistance. The discharge current only flows to the resistance, and this resistance limits the current. This resistance limits the discharging current. The diode does not limit the discharging current. Only the resistance will discharge the current. Right? Will limit the discharge current. Right? This is the complete turn-off snubber circuit. Complete turn-off snubber circuit for the practical case. Now tell me, what is the function of the turn-off snubber circuit? Is the function only for the dV by dt? If the function is only for the dV by dt, so definitely it will reduce the dV by dt. It will reduce the dV by dt because we have connected the capacitance across the device. But what is the remaining function? It will affect on the turn-off time of the device. So the turn-off time of the device has reduced. It has the effect on losses, that is switching losses has reduced, because if the turn-off time has reduced, the losses also reduces, right? The voltage across the switch, during the turn-off also reduced, which is equal to K into Vs. Before that it is, at current equal to 0, it is Vs. If the capacitance is not connected, it is a K into Vs, right? The capacitance is connected, it is a K into Vs. Now, let us see the turn-on snubber. Let us analyze the turn-on snubber. Clear with the turn-off snubber now? So if you have any doubt, you can raise. Otherwise, let us go for the turn-on snubber. Turn-on snubber circuit. Let me take the turn-on snubber circuit here. Turn-on snubber circuit. First, let us draw the basic turn-on snubber circuit. So let me take the switch here. Here also let me consider the two cases. Let me take in case 1, let me take the switch. Here. So in case 1, let me take the switch. So in case 2, so why in turn-on snubber circuit, what is the difference? What is the case here? What we need to keep here? Turn-on snubber circuit, what we need to keep here? Turn-on snubber circuit, what we need to do? So here, if the capacitive load is connected, for example, if the capacitive load or the stray capacitance is connected across the switch, what happens? When switch is in on condition, initially when it is in off condition, the voltage equal to Vs. Assume that initially phi equal to C into dV by dt. So initially when it is in off condition, is equal to Vs. Now I just want to turn on this switch. Assume that when switch is in off condition, whatever be the blocking voltage, this will apply across the switch. Now, so assume that this capacitance is connected to the capacitive load. Or there will be some capacitance effect due to the stray capacitance, that is because of ground and all. There will be some capacitance will exist, right? So let me call this as a stray capacitance. So if the stray capacitance is connected across the switch, what happens during that time? Now I want to close this switch. Now this is an open condition. I want to close the switch. Now I want to close the switch. Before that it is an open condition. Now I want to close the switch. If I close the switch, what happens? The capacitance will. If I close the switch, what is the voltage across the switch? So before that it is Vs. Now it is changed to the 0. I equal to C into dV by dt. I equal to C into dV by dt. So if voltage is changes suddenly in the zero time, so what is the output voltage? What is the current here? So the IC will carry, the capacitance will carry more current. So through the switch, the capacitor current will carry more current to the switch. So due to that, what happens? The switch can damage. The destructive current will flow through the switch, and the switch can be damaged. Now, I need to avoid this sudden change in the current, high value of the current flowing to the switch. So what I have to do? I need to avoid the high value of the current flowing to the switch. What I have to do? I have to keep the inductance here. Let me keep the inductance. I need to keep the inductance. Right? So let me call this as a switch. That is voltage across switch and current flowing to switch. ESW and ISW. Let it be the IL. Let it be the PL here. Voltage across. Now try to draw the switching characteristics for this. How this turn-on circuit will work. So try to get that how this turn-on circuit will work for me. Sir, when started CS and SS? CS will be started soon. Control systems will be started soon. So try to find this. So we need to find how we can find the voltage across inductance here. So try to find. So try to draw the switching characteristics of the switch. Try to draw the switching characteristics for the both cases. Try by yourself so that you will get an idea where the difference is coming. Now let me draw parallelly. Try by yourself also. Here, let me draw the switching characteristics. If I draw the switching characteristics, how the switching characteristics would be. So here, let me take VSW and ISW in the same graph, right? So I need to take the turn-on transition here. So assume that before the device is in the turn-off state. During the turn-off state, what is the voltage? The voltage across switch will be like this. Right? So here, the voltage across switch will becomes to zero. During the turn-on. If I initiate the turn-on process here, will be somewhere it should be. Now slowly the current will increases here, and the current will reach us to the IS. So this is for the first case. For case 1. During the turn-on time, the current slowly increases to the IS and the voltage slowly decreases to the 0. So after completing this turn-on delay, let this delay will be the turn-on delay or turn-on transition. Let me call this as a TR. Now try to draw for the case. What happens? Try to draw for the case 2. So current will not change. That is inductor current equal to switch current. We can take the current as it is. If I take the current, so the current will be same as this one. So the current will be same. Try to draw the voltage across the switch. So current will depends on inductance. Try to draw the voltage across the switch. What is the voltage across the switch? First try to draw the voltage across the switch. So voltage across switch equal to PS is this voltage. PS is the maximum voltage across the switch. So VS is equal to PS. Here it is equal to. Here inductance is added, so that what will do? PL plus VS. PS equal to VL plus VSW. Is VS. Now it becomes to VL plus VSW. Here VS equal to VSW. Here in this case VS equal to VSW, but in this case it will be the VS equal to VL plus VSW. Try to find the VSW. What we'll do here? VSW equal to VS minus V. VSW equal to VL minus V. VS minus VL. That is steady state voltage minus inductor voltage across the inductance. Voltage across the inductance. Now what happens? I find the current. How can I find the current? So VL equal to LdI by dt. L equal to, so it will be the dl by L into di equal to dl by L into dt. L by L into. Now with the VL by L slope, the slope will be the VL by L for the di by dt. If I draw the current, it will depends on, it is inversely proportional, the slope is inversely proportional to the L, so the current slowly increases. The current slowly increases because of the inductance. Because of the inductance, the current slowly increases. The current slowly increases somewhere at this point. Assume that the somewhere at this point it is reaches to the IS. Before that, the current will increase like this. If I kept the inductance increases with this, what happens? The current, because of the inductance, if I choose the high value of the inductance, the time constant will be more. It will take more time to reach the IS value. It will take more time to reach the IS value. Now the load current, the IL will start flowing from this. So what happens during that time? To find the voltage across the switch, the VL also increasing when IL is increasing. If VL is increasing, so the negative portion is increasing, that is Vs minus VL. So what happens? The VSW is reduced. So that what happens if I draw the Vs, up to here it is Vs, up to here it is Vs, that is voltage across switch equal to Vs, voltage across switch equal to Vs. But what happens? So now because of increase in IL here, what happens? The voltage slowly reduces, and somewhere less than TR it will become called as TR. Now this we can mention as a turn on delay. The current, the voltage becomes 0. The current will be. If I find the losses here, the power loss also reduces. So power loss is nothing but VSW into ISW. It will be like this. So here if I find the power losses will be right. Are you taken capacitor as a load, turn on number circuit and inductor as a load? So understand this point. Very good question. So here during the turn on time of the switch, the capacitance effect will affect the turn on time of the switch. Here the capacitance, there will be the two cases are there. So when the circuit is there will be the stray inductance as well as stray capacitance. But during the turn on time, the inductance will not affect the circuit. But the capacitance will affect the circuit. During the turn on, the stray capacitance or the capacitance load will affect the circuit, affect the switch. The capacitance or the stray capacitance will affect the switch. So the circuit contains the load is inductive, or if the load contains, the circuit contains stray inductance, will affect the turn off process. During turn off process, the effect of inductance is more. During the turn on process, the effect of the capacitance is right. But there will be the two cases are there. There will be two will exist. But during the turn on, the capacitance will be affect the switch. The capacitance will be affect the switch performance. Right. Now, so we got the TR dash. Now try to find the L value. How can we find the L value? Try to substitute in this. So VSW equal to, now try to find the VSW. What is the line equation for this? If I take the VL, how the VL would be? So VL equal to VS minus VSW. L equal to VS minus VSW. Now try to, yes, load is same. It is not depends on completely load. It depends on stray inductance, that is stray capacitance. For example, if you take the earth capacitance, so the between the phase and earth also there will be some capacitance. In between the positive and ground also there will be the ground capacitance. That capacitance also, that is, or else if you take the MOSFET, there will be the parasitic capacitance across the MOSFET, right? If you take the MOSFET, for example, let me draw the MOSFET here. It is not the load capacitance. If the load contains capacitance, it is okay. Or else the circuit itself contains the capacitance. If you take the MOSFET, remember that between the drain to source there will be some capacitance. At the junctions there will be capacitance. So here it will be there will be the capacitance exist in between the gate and drain, gate and source. So here it will be the capacitance will exist. So there will be the parasitic capacitance across the device also. These capacitance also will affect the turn-on process. These capacitance will also affect the turn-on process. Right? Now try to find the L value. Try to find the L. Try to find the L value. How we can choose the L value? What is the VSW here? What is the VSW here? What is the VSW here? Yes, you can take the load in both. Load is both for the same cases. Up to here we are clear, right? So ask the doubts so that I can understand how much you have understood. Right? Ask more doubts. So Vs minus VSW. So voltage across switch. If I take the voltage across switch, what is the voltage across switch here? The voltage across switch here, it will be this line. During the turn on condition, so it will be this line. So the current during the turn off process, that TR dash, the current will be, let us assume that is equal to K into IS. So K into IS. Let us assume that which is the K into IS. It is reduced by fraction. Before that, it will be the Vs. Before that, it will be the Vs. Now it is reduced to the fraction. Let us assume that fraction equal to K into Vs. This will be the K into Vs. Right? Now let us find here what is the value of L. What is the value of L? What is the voltage across switch? Voltage across switch equal to Vs into the down line, which has the down slope, which is the 1 minus, it has a negative slope, Vs into 1 minus T by TR dash. So which is equal to VL equal to LDI by dt, EL equal to LDI by dt, LDI by dt, right? So which is equal to Vs minus Vs into 1 minus T by TR dash, 1 minus T by TR dash, right? So 1 minus T by TR dash here, 1 minus T by TR dash, right? So it will be the 1 minus T by TR dash. Try to find the L value from this. Try to find the L value from this. Try to find the L value. So the designed L value, what is the designed L value from this? So the L value will be Ti equal to, so it is varying from the assume that 0 to Kis. So K into Is, dt will be the, so it will be take the dt, so Di equal to, so Vs by L to T by TR dash, T by TR dash, so T by TR dash, so into dt. Now integrate on both the sides. So it is varying from the 0 to K into Is, varying from the 0 to K into Is, and the time is varying from the 0 to TR dash, 0 to TR dash, 0 to TR dash. Now try to find this value. So try to find this value. Try to find the inductance L value. So try to find the inductance L value. Try to find the inductance L value. Now try to find the inductance L value. So K into Is, if I take the L this side, it will be the Vs into TR dash divided by 2, Vs into TR dash divided by 2 to K into Is, K into Is. This will be depends on these parameters. The inductance L value will depends on TR dash and this fraction value, and it will depends on the source voltage. Right? So now let us see, so what is the practical condition of the switch? What is the practical? We have seen the basic. Basic circuit. So now let us see the practical. Let us see the practical snubber circuit. Practical turn-on circuit. Let us see the practical turn-on circuit. Let us see the practical turn-on circuit. So how the practical turn-on circuit? So let me draw the first basic turn-on circuit. Basic turn-on circuit. Basic turn-on snubber circuit. Basic turn-on snubber circuit would be like this. It will be the switch, right? The basic turn-on circuit would be like this. So what is the disadvantage in this? What is the disadvantage in this? Is there any disadvantage in this? So now we have connected. So this circuit is different from the previous circuit. There we have assumed that there will be the stray inductance is there. That is not the load inductance. But Here we are intentionally connect the inductance to limit the di by dt. To limit the di by dt. Here we have intentionally connect the inductance to limit the di by dt. To limit di by dt. Limit di by dt. So to limit the di by dt. To limit the di by dt, we have intentionally connect the circuit, right? Now, what is the disadvantage in this? Can anyone tell what is the disadvantage in this? What is the disadvantage in this? What is the disadvantage for this circuit? This is the basic circuit. Let us implement the practical circuit also. The basic circuit. This is the basic turn-on snubber circuit. The basic turn-on snubber circuit. Maximum voltage across the switch, right? Because we have connected the inductance. Because we have connected the inductance. So what happens here? Initially assume that when the switch is in off condition. Initially assume that the switch is in off condition. So during that time, what happens? During that time, what happens? During that time, what happens? So during that time, so the voltage across during off condition, the voltage will be the Vs. When switch is in on condition, what happens? Initially, the current LdI by dt, right? The current flowing through the inductance will be 0. Initially, the current flowing through the inductance will be 0. Now, if I turn on this inductance, if I turn on this switch, what happens? Initially, the current flowing through the inductance is equal to 0. The current flowing through the inductance, IL not equal to 0. Now, if I turn on the switch, what happens? If I turn on the switch, what happens? If I close the switch, the current will depends on load parameters. Let us assume that it is increased to the IS within 0 time. So what happens? If I find the VL equal to LdI by dt. So within less time, the current is increased to the 0 to IS. So what happens? There will be the large voltage which is induced in the inductance, which causes the voltage across the switch also, because voltage across switch equal to Vs minus Vsw, Vs minus well, that is Vs minus Vl. The large voltage across inductance will cause the large voltage across the switch. So that large voltage will make the switch into the switch. It can damage the switch. Right? Yes. So more voltage will appear across the switch. It can damage the switch. Now what we have to do? Now let us implement the practical circuit. If I kept the L here, let me keep the L here and let me keep the switch here, right? So I need to place the initially the current is flowing like this. When switch is in on condition, if I keep the resistance and diode here, what happens? I keep the resistance. Let me keep the resistance. Let us understand the circuit. Now, how this practical circuit works, let us understand. How this practical circuit works, let us understand. The practical snubber circuit, turn-on circuit will be like this. The practical turn-on circuit will be like this. Let us understand how this practical circuit works. Let us understand. So now, let us understand how this practical circuit works. Right? So now the turn-off process is completed. Assume that the turn-off process is completed. Assume that there will be the turn-off process is completed. The turn on process is completed at this instant. Assume that the turn on process is completed at this instant. Now, after some time, I just want to make this device into turn off. Yes, I just want to make this device into turn off. How can I turn off this device? No, adding the not adding the capacitance. Try to understand the concept. Now, if I add the capacitance, what happens? It will work as a ring circuit. So the energy will be mutually exchanged. That's it. Nothing will be happen. So try to understand. If I want to make this device into turn off at this time. Now understand this. Now the inductance is there. The device got turned on. At this instant. At this instant, the device got turned on. Right? Now, at this instant, the device has to be turned on. Now, what is the current here? IS. What is the current here? IS. Now, I just want to turn off this device. What happens? So the IS current is flowing. So this IS is immediately it has to become to I0, so that the immediate current change within short time will causes the more voltage across the inductor, so which causes more voltage across the switch, right? So we need to avoid this inductance during that time. I need to avoid this inductance. Inductive voltage. How can I avoid this inductance voltage? Let us. If I connect the diode here. Assume that. So initially it is in the on condition. So the inductor has some energy which is equal to half into Li square. The inductor has some energy. Now initially it is in turn on condition, so it has some energy. It stores some energy which is equal to half into Li square. Now if I want to make this into off condition, what happens? What will be the stored energy in the inductance? Now before that the polarity will be like this. Now what is the voltage polarity here? The voltage polarity will change. Because switch is an off condition. Now this inductance is trying to dissipate its energy. So what happens? Now this diode is in the forward bias condition. Diode is an on. So where there should be some energy dissipating element also, so that I will keep the resistance here. So whatever be the energy stored in the inductance will start flowing like this, will dissipate in the energy is recovered in the, whatever be the energy stored in the inductance, it is recovered by the resistance. Because of that, we will keep the resistance and diode. The complete circuit will be the resistance and diode. Right? Is there any doubt? Till now, is there any doubt? Now, try to draw the complete snubber circuit. So try to draw the complete snubber circuit for the SCR, which is the combination of turn on and turn off snubber circuit. So try to draw the complete snubber circuit for SCR. So now let me take Thyristor here. Now, so try to draw the turn off snubber circuit. What is turn off snubber circuit? So try to draw the turn off snubber circuit. What is turn off snubber circuit? So the turn off snubber circuit is nothing but, so the capacitance has to be connected across this. Right? The capacitance has to be connected across this. And the resistance also should be connected to discharge current. Right? So the capacitance also should be connected here. So that capacitance and the diode and the resistance. Right? The capacitance, diode and resistance. The turn off snubber circuit is sometimes it is also called as RCD circuit. RCD snubber circuit, which is also called as RCD snubber circuit. the turn-off snubber circuit. Sometimes it is called as RCD snubber circuit. Now try to draw the turn-on snubber circuit, which is the turn-off snubber circuit. So try to draw the turn-on snubber circuit. How can we draw the turn-on snubber circuit? So for turn-on snubber circuit, we need to keep an inductance here, right? Across inductance, we need to keep the resistance and the diode. Resistance and the diode. This is the turn-off snubber circuit, and this is the turn-on snubber circuit. The turn-on snubber circuit. This is the turn-on snubber circuit. Is there any doubt till now? Is there any doubt till now? Is there any doubt till now? Let me summarize up to here. So whatever be the content we have delivered till now. So let me summarize all this. Let me summarize all the topics. So that if you have any doubt, you can ask in middle. Where we have started, let me summarize in 5 minutes. So where we have started. So why the protection is needed? Why the protection is needed? So the answer is so to make the device into safe operating area, that is Pmax, Imax, Pmax, voltage, maximum current, maximum power and temperature, maximum temperature limit. So the device should be in this safe operating area to make the device to operate in the safe operating area. And the second point is, so to make the device dV by dt and di by dt values into the safe region, that is specified limits, to the maximum limit. So if it is not maintained, what happens? It is not maintained, what happens? So because of dV by dt, there will be the false triggering will be happen. So because of di by dt, there will be the current grounding will be happen. Right? So the next one. So energy loss by power loss. So what is energy loss by power loss? So the energy loss will be depends on the switching transitions, because the energy loss will be during conduction losses as well as the blocking mode. The energy loss will be less. The energy loss will be more during the switching transitions. So that we will consider the switching transition period. If the more transitions are there, a cycle, what happens? The energy loss will be more. Due to that, what happens? The temperature increases. The temperature exceeds its limit. What happens? The device can damage. So we make sure that for the energy losses, we make sure that the temperature limit also we should consider, right? So last point what we have taken, when the switch with anti-parallel diode is there, the switch turn on and turn off time will be depends on the forward recovery time and the reverse recovery time. Forward recovery time and reverse recovery time, right? So in a snubber circuit, we have the two types of circuits: turn on snubber circuit and turn off snubber circuit. The turn on snubber circuit is for the dV by dt protection. The turn off snubber circuit will be for the dV by dt protection. The turn on will be for the di by dt protection. So it is for di by dt protection, and the turn off snubber circuit for the dV by dt protection. dV by dt protection, right? Right. So what happens here? So during the turn on snubber circuit, we will add the basic capacitance. From that capacitance, if you observe that, what happens? The turn off delay time has reduced, so that the power loss also reduces, as well as because we have kept the capacitance, it does not allow the sudden change in the voltage. So if you observe this curve, you can find that it is not allowing the sudden change in the voltage, right? From that, we have implemented the practical circuit. In a practical circuit, how it would be? It contains resistance and diode. This resistance is to limit the discharge current. Diode will allow this diode will bypass the resistance during the charging current. What this diode will do? This diode will bypass the charging. This diode will bypass the resistance during the charging time. What is the function of resistance? This resistance will limit the discharge current, right? Now let us see. So which is the turn on snubber? Which is the turn on snubber circuit? In case of turn on snubber circuit, so we should limit the di by dt, so that we will keep the inductance. Because if you kept the inductance, what happens? The TR, that is on time delay time, has reduced. On time delay time has reduced. The power loss also reduces. The power loss reduces, as well as what happens? So the voltage and current are kept in specified limits, because when it is in on condition, the current is reduced, right? The current is reduced. That the voltage and current also kept in specified limits, as well as power loss has reduced. So power loss has reduced. If the power loss, if it is reduced, if this time is reduced, the device will operate in the specified temperature limits, as well as di by dt also reduces, right? So how the practical circuit has implemented? The practical circuit has implemented, how the practical circuit has implemented by using the diode and resistance across the inductance. If I kept the diode and resistance across the inductance, whatever be the stored, whatever be the voltage, high voltage, what happens during this condition? This diode will be in on condition. So whatever be the energy stored in the inductance, which will recover through the resistance, right? This is the complete snubber circuit, which is the combination of turn on snubber circuit and turn off snubber circuit. Right? Let us solve the problems. Let us solve the problems on snubber circuit. So this I will take in the next class. Otherwise, I will schedule the special class for the problems on snubber circuit. Try to attend the session. Right? Thank you so much, guys. Thanks for attending the session. Thank you so much, guys. Thanks for attending the session. So do subscribe and like. So share the session. Let us reach it to the maximum. So still, if you have doubt, you can ask. Otherwise, let me end the session. Still, if you have doubt, you can ask. Otherwise, let me end the session.